Hi, welcome to my channel again. So for this video, I'll be explaining how this flyback plus Xavier circuit works. So let's get started. So first, I'll name the component's name. This is called a tank capacitor, and this is the choke, and this I use two chokes for better protection. This is called a MOSFET, which is IRP 540 MOSFET, and this both tank cap equals 0.94 UF total. And this is a fast recovery diode on the MOSFETs, and this is a 10K resistor. This is a 12 volt Zener diode, and this is 220 ohm resistor. So these are the components names, and I have used a 5-turn primary on this flyback outer core to drive the secondary. So now I'll tell you about the components purpose. So let's start first with this thing. This is called a choke, and this is used to reduce the flyback. So this is used to reduce the spike of the flyback when it's operating at kilohertz frequency. So this why this used is when this primary oscillates at 60 kilohertz, which roughly equals, so which means that the positive and negative terminals switch 60,000 times per second, and remember 60,000 times per second. And when it oscillates at that kind of frequency, the secondary can easily give a spike through the primary, which can easily damage the MOSFET source and ground. And the reason the chokes are in the both of the drains of the MOSFET is the primary is also connected to the primary is also connected to the drains of the MOSFET. So when the spike comes, the spike will not go to the MOSFET ground or the source, but if it goes to the MOSFET ground and source, it will get easily damaged and the circuit will not work. So if adding a choke means the current will go through the chokes, and through current will go through the choke and reduce the MOSFET's failure possibility of failing, and that's why these chokes are for. So now let's talk about the tank capacitor. And this is a tank capacitor of, and one tank capacitor consists of 0.74 UF, and I used two caps which equals 0.94 UF in total. and and this is called a LC resonant tank capacitor, and this is you and this tank capacitor charges and discharges every time the circuit's primary gets switched. So if it gets switched one time, the tank capacitor will get charged, and when it switches to the other, the tank capacitor will discharge, and that's what these tank capacitors are for. So now let's move on to the main component of the ZVS, the MOSFETs. This is IRP 540 N-channel MOSFET, which is the best MOSFET that could. This might be not the best MOSFET that you can use for ZVS. I'd recommend using a IRP F260 N-channel MOSFET, which can handle more constant amperes, and it can handle much voltage than these MOSFETs. But these MOSFETs are common than those big MOSFETs, so if you're in a budget, you can use those MOSFETs as well. And these help to switch the primary at kilohertz frequency. And these are the purpose of the MOSFET. So now let's move on to the resistors, 10K resistors. And this is a pull down resistor. This is used to do when the MOSFET turns on and off. Some little charge will always stay in the MOSFET. So when the resistor charge, well, this MOSFET is off and this MOSFET is on, that will create a short circuit, which that we don't want. So adding a 10K resistor right here will discharge the MOSFET right after when it's off. So this MOSFET gets switched on correctly. And that's the reason why I added this 10K resistors. So now let's talk about why the Zener diodes are present. The Zener diodes, they are 12 volt ratings, 12 volts, 12 volts and 1 watt. Yeah, and the reason that these three diodes are present here is when the MOSFET when the MOSFET gets power, the the frequency can easily exceed 20 volts. Easily exceed 20 volts. The MOSFET max ground TS voltage rating is just 12 volts. If it goes above 12 volts, the silicon inside the MOSFET will break down and you might not get, and the circuit will fail immediately. That's why putting the Zeners will reduce the MOSFET G and S current to maximum to 12 volt, and that will helps to keep the circuit at good shape. That's why I used two Zeners on both of the MOSFETs G, ground and source. So now let's move to the diodes, and this is a UF700 UF700 fast recovery diode, and this is used to control, and this is used to bottom some of the switching. So when this MOSFET turns on, it will send a signal to the D pin and to the MOSFET's other leg source, and when this MOSFET turns off, and this MOSFET turns on, and this MOSFET has a other diode on its D pin which goes to the other MOSFETs. I mean the source pin, and this goes to other MOSFETs D pin. And this cycle just repeats itself and creates 60 kilohertz on the primary, and that are the purpose of these pots. Now let's move on to the 220 ohm resistors, and this is used to switch the, and these MOSFETs can do above 60 kilohertz, and if it goes up 60 kilohertz, it can go above 60 kilohertz, but it cannot handle that 60 kilohertz frequency. This might sound confusing, but these resistors are used to reduce the frequency. You might think like, no, reducing the frequency will affect the performance, but 60 kilohertz is enough to drive this flyback. If this MOSFET oscillates above 60 kilohertz, it will ring and it will just die of too much oscillation. That's why adding this 220 ohm resistor on both of the MOSFET source pins, the frequency gets reduced to the right point where the flyback operates correctly, and that's the reason these 220 ohm resistors are present in these flybacks CVS. And let's talk about the flyback now. And this is I have wounded 5 turns of primary, and this might not seem like 5 turns of primary because there are so many calls, as you can see right here, because I used it in a way so you can have low power mode and high power mode. When I disconnect, so to get low power mode I have to disconnect this wire and take this small thin wire and put it on the MOSFET D pin right here. If I put it on there, then the circuit operates at a lower hertz, which will output less voltage, but that kind of voltage can be easily used use for ozone generators. That's why I use 2 modes right here. That's the reason. And so now let's talk about the flyback sign. The flyback sign is around about like 60,000, more than 60,000 of thin super thin copper wires on the secondary. And when the primary is 5 and the secondary has a larger inductance than the primary, the voltage builds up. That's the principle of this flyback. So low inductance on the primary and high inductance on the secondary equals step up voltage, and this flyback can easily step up the voltage from 14 volts to 66,000 volts DC. You cannot call it pure DC because it's little pulsed and unpredictable pulses. It's usually because of the high voltage, I guess. So when this flyback powers up, you will get white or purple or even red arcs if your current rating is too low. So the reason the arcs are differs from voltages. When you get white arcs on the secondary, it means that high current is flowing to the secondary output, which will ionize the air, and the air will get hot, and the air will get hot and get white, and the arcs will get white. It's due to the rapid voltage buildup, I guess. And that's the principle of this whole Xavier circuit. It might sound a little complex, but it's understandable. Like, if you have the interest, you can easily learn this. If you don't have the interest, it's pretty hard to learn about this. So by the end of the video, I'd like to show my flyback working. So let's start the arcs right here. As you can see, the arcs are white, arcs are white and purple, so it's roughly 8000 degrees Celsius on the arcs. And that's it. Take care. Bye bye.